Yeah, that's the way to do it. All right, so exam 2 is Monday. And the topics are everything up through particle kinetics. And so today I'm just planning to work on, answer questions, homework questions, and go through particle kinetics examples and that kind of stuff. Anybody have any questions about the test first? Anybody have any homework questions? Oh, yeah. Yeah, I'll give every equation you need will be on there. Yep. It depends what kind of questions they are, but I'd say 4 is usually a pretty good guess. Yep. Yeah, something like that. Yeah. Any other questions about the test? Okay. Any specific homework questions you want to see? 14? Okay. So it's a 5-kilogram object. And it's in spherical motion, so it's moving around a 3-dimensional path where distance from the center of the sphere to the outside is 2 meters. It has a constant angular acceleration of 0, 4, -8. And at time 0, the angular velocity vector is 500. This is radians per second squared, the angular acceleration. The angular velocity is radians per second. And at time 5, the r vector, so the vector going from the center of the sphere to the object, is 0, 0, 2. We want to calculate the angular velocity as a function of time. The velocity vector when time is equal to 5 seconds. The acceleration vector when time is 5 seconds. And the net force on the object when time is equal to 5 seconds. Okay, so the Newton's second law says that once we know that acceleration vector at 5 seconds, all we have to do is multiply by the mass to get the net force. All right, so first of all, the relationship between, so you can think of the definition of angular acceleration as a function of time is the time derivative of the angular velocity as a function of time. So that says that um, we can calculate the angular velocity as a function of time by integrating the angular acceleration as a function of time with respect to time. So that's what we have to do for part A. We have a constant angular acceleration of 0, 4, negative 8. So we're going to integrate 0, 4, negative 8 with respect to time. That just means that you integrate the individual components. So, all right, this is a constant representing x. Then we have 4t plus a constant for y, and then negative 8t plus a constant for z. We need to know those constants, and so now we need to use the boundary condition. And the boundary condition we're given for omega is that at time equals 0, we know what omega is, 5, 0, 0. So the boundary condition says when time is equal to 0, omega, which is this thing we just calculated, is equal to positive 5, 0, 0. So that lets us calculate Cx, Cy, and Cz. So Cx is 5, Cy and Cz are both 0. And now we can plug that back into, this is our angular velocity as a function of time. So angular velocity as a function of time is 5, 4t, negative 8t. Any questions about that? And then for B, we want to calculate the velocity vector when time is equal to 5 seconds. Well, the velocity vector at any instant is equal to omega crossed with the r vector. We can calculate omega by just plugging in 5 seconds into our function for angular velocity. So omega at 5 seconds is equal to 5, and then 4 times 5, and then negative 8 times 5. So that angular velocity vector is 5, 20, negative 40. This is in radians per second. And we're given the r vector at 5 seconds. That's 0, 0, 2. Meters. And so now we can just plug that in, and the velocity vector at the time 5 seconds is equal to 5, 20, negative 40, crossed with 0, 0, 2. And so you get 40, negative 10, 0. Any questions about that one? Now we're going to do the same thing for the acceleration. So the acceleration, the equation we're going to use is the watermelon equation. So this is equal to alpha cross r plus omega cross quantity omega cross r. All ripe watermelons will rot. And we know that the angular acceleration is the same at all times. It's 0, 4, negative 8. And we already have omega and r at time equals 5 seconds. So the acceleration when time is 5 seconds is equal to 0, 4, negative 8, crossed with 0, 0, 2, plus the omega that we got in part B, 5, 20, negative 40. Crossed with the quantity 5, 20, negative 40, cross r vector 0, 0, 2. This we just did in part B, the stuff in the parentheses. So this comes out to be 40, negative 10, 0. And so we're going to cross that with 5, 20, negative 40. And we're still adding that too. So this one comes out to be 8, 0, 0. And so the total acceleration evaluated at 5 seconds is, well, we got 800 plus negative 400 negative 1600 and then negative 50 minus 800 so minus 850. And so put these all together, you get negative 392, negative 1600, negative 850, and this is in meters per second squared. And that's the total acceleration at that instant. And then the last question, part D, is just asking for the net force. Well, F net is equal to the mass times the acceleration. So that's equal to 2 times this vector we just calculated. Kilograms? Oh yeah, 5. Thank you. negative 1600, negative 850. All right, so that's 1960 negative and 8,000 negative and 4 negative 4250 newtons. Any questions about that one? Yeah. I do it, I divide it by 2 and then multiply by 10. Any other questions? Doing stuff fast in your head is like totally worthless, except it makes people think you're smarter than you necessarily are. Yeah. Yeah, sure.
Are there any problems that we don't have to worry about, like number 7 you had mentioned yesterday? Because lesson
Yes.
4 regarding studying it.
Yes. Okay. Yeah. Thank you for. I did mean to mention that. Okay. Number 7. Well, that is a pretty complicated system that you also have to use relative motion for. If I had a relative motion problem, the system that would be in that you had to do with relative motion would not be that complicated. Um, so, uh, so like the thing with, and I wouldn't make you think on the fly about. So when I say the system is complicated, I wouldn't make you think during a test about like if you pull this down this far, this is going to go up some fraction of that or some multiple of that or whatever. I wouldn't make you. So um, if there's any system like that, the way that it would be simpler is that all you'd have to think about is directions. One thing moving this way some amount would mean something else moving the same amount in some other direction. Okay. Um, so maybe in a minute I can do an example of sort of a simpler version of that. But like I'm thinking of like the one that I did last class, if you just a simpler version of number 7 would be like instead of 2 pulleys, there'd just be one mass, a cable, and then another mass over the pulley. And so one going up just means the other one goes down that same amount. But yeah, you should be able to figure out how to include relative motion into a simple system of things moving. Okay. Yeah. Okay, number 8. Uh-huh. Oh, okay. Okay, it's up in my office. We can get it after. So it's a 3-kilogram object. And it's on a path. Position is equal to x squared. Another way to describe that path is that f of x is equal to x squared. Those two mean the same thing. But the vector is what we want to, this is sort of gets us from like one step closer to how we want to do this. And the speed is 8 meters per second the whole time. this position vector is given in meters, and we want to know what's the net force on the object. Um, when x is equal to 2 meters. Well, one thing about this is uh, there are different answers for which direction the object is moving along that path. So I guess technically, if it doesn't say which direction it's moving, you should give both answers. I mean, really, it just means that I forgot to tell you which direction it's moving. You know, so I need to do that. On the test, I need to say it's moving in the positive or negative direction. Let me just let me say negative direction so you see. Okay, so let's say it's moving in the negative x direction. Okay, so what this means is, okay, here's the path. The object's moving along that path. What's the net force on this object at x equals 2 over here somewhere? Well, if the object's moving 8 meters per second like that, clearly the net force is going to be different than if the object's moving 8 meters per second that way. So that's why you need to know that. And it comes into it when you're calculating that unit vector that's tangent to the path. So I'll show you where that is. But for us, we're going to be saying that it's moving this direction along the path. Anyone have any kind of guess about what that net force is going to be? So this is important. So that is a really easy thing to think. I mean, and because it's moving at 8 meters per second constant, right? So it's not speeding up or slowing down. But remember, velocity is a vector, and there's non-zero acceleration as long as the velocity is changing. And a vector is changing even if it's only changing direction. Think of like centripetal acceleration in circular motion. So there is one part of the acceleration that's going to be zero. That's the part that's tangent to the path. Okay? So there's not going to be any acceleration tangent to the path. There's only going to be acceleration that's making it turn, and so that's going to be sort of like, this isn't a circle, but it's kind of like the equivalent of centripetal acceleration. So it should be pointing that direction, if I'm thinking about it right. Okay, as far as like a sanity check for when we're done, we can check our answer against that. It should be somewhere in the second quadrant. You know, negative x direction, positive y direction, and it should be quite a bit bigger negative x magnitude than positive y magnitude. Yep.
Now, why are you unsure? Isn't it just always toward the center of the sort of circle?
Yeah. Yes, that centripetal acceleration. Yes, I should be sure.
Okay.
You're right. I should be sure. But I just thought of that right now to say so. I'm just. But so if we get an answer with a big negative x and a small positive y, then I'm going to feel pretty happy, because that's what I expect. All right, so what do we have to do? We have this parameterization. What we're trying to get to is we know that if we come up with the velocity vector as a function of x, then we can use the chain rule to come up with the acceleration as a function of x. And so to get a vector that's tangent to the path, we're going to take the derivative of both of these with respect to whatever parameter you have. In this case, it's x. So I'm going to go d dx of x squared. And then we're going to have to, so that would give us a vector that's tangent to the path in the direction of increasing whatever the parameter is. So in this case, increasing x. We want negative because it's moving in the direction of decreasing x. Okay. If it was moving in the positive x direction, then you would just leave that alone. So we get a vector here that's 1, 2x. Is that a unit vector? No, I mean, it is for one specific x, but we need this expressed as a unit vector function of x. Like we need it to be a unit vector for every x value. So now to normalize this, I'm going to divide it by the magnitude. And so we get, oh, I still have this negative here. And so we get negative 1 over, the magnitude is 1 plus 4x squared square root. And then the y component is negative 2x over that same square root. Okay, so that's a unit vector that's tangent to the path in the direction of decreasing x. Okay, so what we have here is this. And I'm going to write that as negative quantity 1 plus 4x squared to the negative 1 half, and negative 2x times the quantity 1 plus 4x squared to the negative 1 half. And then our velocity vector, we know this is the direction of our velocity vector, and we know the magnitude of the velocity vector is 8. So we'll just multiply to get the velocity as a function of x. Just multiply this by 8. So we get negative 8 times the quantity 1 plus 4x squared to the negative 1 half, and negative 2x times the quantity 1 plus 4x squared to the negative 1 half. Oh yeah, thank you. Okay, so that's the velocity vector at whatever x value. That tells you what the velocity vector is. So if you plug in x equals 0, it tells you the velocity vector here. If you plug in x equals negative 2, it tells you the velocity vector here. Okay. And now the acceleration is a function of x. We know that it's equal to dv dt. That's the definition. That is never wrong. But we don't have it as a function of t, so we have to use the chain rule here. So this is dv dx dx dt, which is dv dx, and then dx dt is like our x component of that velocity. Okay, so this derivative is kind of ugly. So dv dx is negative 1 half times negative 8, so that's positive 4 times 1 plus 4x squared to the negative 3 halves. And then you have to use the chain rule to take the derivative of the stuff inside the parentheses. So that's times 8x. And for the y component, we have to use the product rule first. So we have negative 16 times the quantity 1 plus 4x squared to the negative 1 half. And then we have plus 8x times the quantity 1 plus 4x squared to the negative 3 halves times the derivative of the stuff inside the parentheses, which is 8x again. And so now we can evaluate this at x equals 2. So 16, 17, so we have 4 times 17 to the negative 3 halves power times 16. That's the x component. The y component, we have negative 16 times 17 to the negative 1 half. Yeah.
Why did you multiply by AX instead of
This, all of this, I'm just still calculating that derivative. This is using the chain rule to calculate the derivative of 1 plus 4x squared with respect to x.
you haven't multiplied by?
Right, I haven't done that yet. So negative 16 times 17 to the negative 1 half, and then plus 16 times 17 to the negative 3 halves times 16. Okay, so that's that derivative. X component of the velocity evaluated at x equals 2 is negative 32 times 17 to the minus 1 half. And so multiply these together and you get the acceleration vector at x equals 2. I went back to the velocity function. So, oh, I did the y value, yep. So negative 8 times 17 to the minus 1 half. And so you get negative 8 times 17 to the negative 1 half times this vector, 4 times 17 to the minus 3 halves times 16. And then the y component is negative 16 times 17 to the negative 1 half plus 16 times 17 to the minus 3 halves times 16. And we're looking for, well, that's the acceleration. And then to get the net force evaluated at x equals 2, that's just going to be the mass of this is 3. So this is just going to be 3 times that acceleration. And if you plug all those numbers in, like calculate the components of this thing, I definitely can't do that in my head. You should get a big negative x value, and you can see that it's negative anyways, and a smaller positive y value. And it looks like that'll be positive. Well, it's hard to say.
This last statement, what does that mean? F net evaluated x equals 2 equals 3.
Yeah, because it said that the mass of the object is 3 kilograms. So this is the mass. Yeah. Yeah. Well, the definition of the acceleration is the time derivative of v. But we didn't have it expressed explicitly as a function of time, so we had to use the chain rule. Yeah. And yeah, so that vx is just the dx dt. I really slide it up. I really don't have anything to say about that. I mean, if would anybody feel happier getting another few classes, another week or something before you got tested on this stuff? You want more time to? Well, conceptually, yes, it could be, but the difficulty of of doing the mechanics of it wouldn't be, because it would take the whole test, and I want to put more than one question on the test, but well, is is anybody have any concerns about moving the test back a little bit? It's more what? The speed of the what? Oh, yeah. Well, I mean, it always helps to absorb stuff for a little longer. Um, and I'd be happy to move the test on this stuff back. But yeah, like the more we move stuff back, the more stuff that's going to be on the next exam. Yeah, yeah, yeah. At the weekend. Yeah. So as far as, yeah, like I guess I don't have any. I don't really have any. I can't really point towards anything. All of these concepts need to be fair game on this test. Um, as far as like the individual problems have to be like a little bit simpler versions of any of these, because I have to fit 4 questions in a 50-minute exam. Yes. Um, I don't off the top of my head. I think it was pretty good. What? Mid 80s? Yeah. Okay. Well, yeah, just, new material instead. Yeah. Yeah. So I'd say, I guess, as far as getting ready for this stuff, I would try to identify like some of these take pages of calculations, and that's a little ominous or whatever. But what you need to do besides getting the practice that comes with the pages of calculations in doing those calculations, I think, with these questions as you do them, just try to identify like what are the steps that are happening in that problem that make it special compared to the other ones, Like this is it really is just a chain rule problem, It's, and we did those kind of problems in particle kinematics too, And so I think largely it's just like identifying the big picture of what each problem is about, Like this one, you look at it and you're like, okay, I mean, hopefully you look at it and you think, okay, well, um, we're given the path as a function of x, and so we're not going to be able to take the time derivative, but you've done problems before where you've used that chain rule approach, come up with the velocity vector, use the chain rule to find the acceleration. And so, if you can identify the set of steps that each problem is going to require, then that's really the main name of the game for the test, I would say, and the actual derivatives are going to be gentler than this because they have to be on a 50-minute test, uh and just have a little more time. Okay, so let's do that. Let's do it middle ground. Do it on Wednesday. If that doesn't work for anybody, send me an email. If you'd rather take it on Monday, I can arrange that. But let's do it in class on Wednesday. Done. What? Yeah, just give me the binders after you take the test. Okay. That's all then. Have a good weekend.